Every single digital transaction, search query, and complex automated system relies heavily on an invisible layer of physical infrastructure. Recently, a single hardware manufacturer bypassed established giants like Apple and Microsoft, with its valuation briefly hitting $4 trillion. The modern computing ecosystem routes through their specific silicon bottleneck. Medical imaging, global logistics, and generative text models all funnel directly through their specific components. How did a firm that never launched a social network, a smartphone, or a search engine become the architect of the digital age? The answer does not start with a recent artificial intelligence invention. It traces back 30 years to a gamble made in a roadside diner. Jensen Huang spent his youth cleaning bathrooms at a Kentucky reform school before working graveyard shifts washing dishes at a Denny's. In 1993, he co-founded Nvidia to solve a specific problem, accelerating the rendering of 3D graphics for video games. Their first product, the NV1, relied on proprietary curved surface technology that failed in the market. That near collapse established a corporate culture of intense paranoia and rapid iteration. Standard computing relied on the CPU, like one professor solving a single math problem. In 1999, Nvidia introduced the GPU, processing data through thousands of simultaneous lanes. This parallel architecture had one purpose: calculating millions of geometric triangles at once to render video game frames. By surviving the hardware cycles of the 1990s, Nvidia perfected a massively parallel mathematical engine. Ultimately, they had successfully built an incredibly powerful tool that was just waiting for a problem to solve. By 2012, researchers understood the theory behind neural networks, but practical progress was stalled. Scientists lacked the raw compute power to process the massive datasets required to train deep models. A team from the University of Toronto entered a massive visual recognition competition, facing the task of training a model containing 60 million parameters. A moment of realization. They noticed that the matrix multiplications required to calculate a neural network's weights are virtually identical to the math used to shade pixels on a screen. Using two consumer GTX 580 gaming GPUs, the researchers slashed their training time from several months to 5 days, achieving an error rate that doubled the accuracy of their competitors. This success proved that feeding datasets into parallel computing arrays outperformed human-coded logic, triggering the modern AI gold rush. Hardware alone did not secure their position. In 2006, Nvidia released CUDA, a software platform that allowed scientists to program their graphics cards using standard C++ code. Huang insisted that CUDA support be integrated into every single GPU sold. This put a personal supercomputer into the hands of thousands of university researchers. An entire generation of academics learned to write algorithms exclusively in this proprietary language. Today, competitors find it difficult to lure developers away from a codebase they have used for nearly 2 decades. This chart shows the company's data center revenue trajectory. The figure jumped from $47.5 billion in fiscal year 2024 to an estimated $193.7 billion by 2026, accounting for 90%. These processors have moved beyond the consumer market to become critical national security assets. Governments now view advanced silicon manufacturing as a pillar of global power. Competitors are gaining ground. AMD's MI350X chip matches Nvidia on raw processing power, while offering higher memory capacity and a lower price point. A larger threat comes from the major cloud providers. Google and AWS are designing their own custom AI silicon to bypass external suppliers and recover their profit margins. Nvidia maintains its position through an aggressive annual release cycle, pushing manufacturing partners like TSMC to continuously advance fabrication limits. Even as cheaper hardware alternatives reach the market, 18 years of software maturity and ecosystem integration keep the global economy firmly locked in. Historically, data centers functioned as passive warehouses for emails and photo backups. Today, they operate as AI factories, facilities that ingest raw data to actively manufacture new intelligence, insights, and economic value. These facilities are becoming cognitive, using physical AI and digital twins to predict maintenance and automatically manage their own power and cooling requirements. Nvidia now delivers integrated sovereign AI systems to national governments, bundling their hardware with custom networking and software. The company engineered the operating system for the next industrial revolution. By surviving the demands of 1990s video gaming, they built the mathematical engine currently rendering the infrastructure of the human future.